by looking at characteristics. For example, these particles might have certain properties, such as timing, which might be different from the standard model particles. So by designing detectors which can very, very precisely go after timing, you might be able to go after the long-lived particles. Some of it, the high luminosity LHC can do, but it was never designed to do exactly that. So now we have the opportunity with our future experiments to really design them in such a way that we can focus on extracting this new physics.
Greetings, I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations today as a GBH Forum Network webinar. Our immense universe began at the tiny quantum scale, and to understand how matter formed, then physicists collide subatomic particles. The Large Hadron Collider, known as LHC at CERN, has produced many discoveries, including the Higgs boson, but there are limits to the range of data it can capture. Dr. Tulika Bose, who is prominently involved in the work of the Large Hadron Collider, says we really should be looking at new physics at much higher scale. We really need to go beyond the kind of energies we have at the Large Hadron Collider. And in this presentation, Dr. Bose will describe a 10-year strategic plan for U.S. particle physics, which is centered on decoding the quantum realm, unveiling the hidden universe, and exploring novel paradigms. Tulika Bose is a Willis Distinguished Achievement Professor of Physics at the University of Wisconsin-Madison and is currently serving as the Deputy U.S. Compact Muon Solenoid CMS Software and Computing Operations Program Manager, that's a mouthful, at CERN's Large Hadron Collider. She has served other major coordinator positions at the LHC in the past. Of special importance for today's presentation, Dr. Bose is a member of the Particle Physics Project Prioritization Panel, known as the P5, a scientific advisory body tasked by the Department of Energy and the National Science Foundation to develop a strategic plan and vision for U.S. particle physics for the future. And so we are honored to welcome Dr. Bose today. Thank you very much for joining us, Tulika Bose.
Thank you very much, Yvonne, for this very kind introduction. It's a pleasure to be here today to talk to you about new directions in particle physics. All right, with that, let me get started. So I'm going to talk about new directions in particle physics. So of course, perhaps to start off, I should mention what particle physics is in my context. So it is the study of the smallest known building blocks of the physical universe and the interactions between them. The focus in this case is on single particles or small groups of particles, such as the one that you see there in that cartoon, and not the billions of atoms or molecules that make up an entire planet. Now, how do we study particle physics? I'm just going to give you one example of doing so, and this is by using what are called colliders. I'm a collider physicist. And to understand how we do this, you can take the example of, I have two tennis balls, and I accelerate them, so put in a lot of energy into them, and I make them collide and come together. So something like this. Now, what you saw out of this collision was a lot of crazy stuff emerging, and in fact, what you saw that these collisions at high energies produced more massive particles than what went in. You produce these big basketballs and bowling balls out of the tennis balls. So that's the principle, using Einstein's E is equal to mc squared, putting in a lot of energy, producing mass out of it. Of course, this is a cartoon, and unlike in this cartoon, the collisions that we study obey specific quantum rules. But these sort of machines, these colliders, have been really used very effectively over the course of the last 50 years to really study in great detail what are called elementary and composite particles. These particles comprise what is called the standard model of particles and forces. That's the picture here on the left, which shows what are called 3 generations of particles called quarks and 3 generations of particles called leptons or light particles. And the yellow ellipse really shows what are called the first generation particles, which is what most of the universe is comprised of. These quarks have interesting names, such as, for example, up and down, strain, charm, top and bottom, and the leptons are electron, muon, and tau, and then their corresponding neutral particles called the neutrinos, which is what you see here. Also, an important part of the standard model are the fundamental forces. There is a force of electricity and magnetism, and the electromagnetic force that most of you are probably aware of from your day-to-day lives. And this force is mediated by the particle we call the photon, which is responsible for sort of carrying the force or mediating the interaction. Also, there is a strong force, which is responsible for holding nuclei together. And that's mediated by this particle called the gluon, denoted by G. And then there is the force of what's called the electroweak force, or the force which is responsible for radioactivity, beta decay. And that's mediated by these particles that are called the W and Z bosons. Now, all of this came together sort of in the mid-1950s and 60s, and mostly it was working well. And in particular, it worked very well, the theory understanding, for what are called massless particles, such as the photon and the gluon. However, when we started looking at and measuring masses for many of the other particles, including the particles that you see here, the quarks and the leptons, but also, for example, the W and Z bosons, it was realized at that point that the standard model didn't really have a clear understanding for why these particles had the mass that they had and why there was such a large range of masses. So in order to understand that, there had to be new theories that came about to explain that. And this resulted in the understanding that perhaps there is a particle, and this came famously to be called the Higgs boson, even though there were several people named after Peter Higgs who was responsible for theorizing this particle, though there were several other people who independently at the same time came to the same conclusion. So this Higgs particle, in a way, was associated with the mechanism that would give particles their mass. So then the question is, how does it actually do that? In order to understand that, it's useful to look at, I always find, a couple of analogies. And then the first of these starts with this parachute, say, that you, at the very top out of an airplane, you want to jump off, and then you have a parachute. So the question I would have for you is, which of these would be your preferred option, which is that you fall slower and safely down to the ground, an unopened parachute or a fully opened parachute? Well, the answer, I think all of you clearly know in this case, is a fully open parachute. Because what happens? Well, the parachute, when it is fully open form, interacts with all of the medium air around us. And this interaction lowers the speed of the drop, and you sort of come very safely down to the ground. So this interaction is what is important. Similarly, or analogous to the air, you have the Higgs field, which is responsible for sort of permeating all of space, and particles interact with this Higgs field, and the amount of interaction is different, or rather it has different strengths. When it interacts more, as in the case of the fully open parachute, then it seems to have more mass and hence is slowed down. When it interacts very little, it's almost like it is massless and it whizzes through and falls, maybe in an unsafe manner to the ground. So the higher the interaction, the larger the particle's mass. there's a famous set of cartoons that sort of tries to convey the same information. So I like to do that because I think it was interesting that this was the British Prime Minister back in the day, Margaret Thatcher, who wanted to understand the Higgs mechanism, and a professor at University College London came up with this idea. So imagine a room full of what they call party workers. We can just think it's a standard party, let's say. And people are sitting around or standing around talking to each other. And then a famous person enters through the door of that room. And this was, Albert Einstein. You can think of Taylor Swift in today's, era. And as this famous person walks through the door, what's going to happen? Well, everybody is going to start like looking around and wondering and sort of will start clustering around that person because they'll be like, why are you here? What is your purpose? And what are you up to? And so if that person, say, is trying to get through to the very other side of the room, they will be slowed down because all of these people are surrounding them, asking them questions. So this slowing down almost seems like they've acquired in mass. And because, more massive particles move more slowly. So they're interacting with the crowd. And the larger the interaction, the more massive they appear and are, in this case, slowed down. But it's the more mass that is what results. On the other hand, imagine that a complete nobody walks through the door. Well, nobody's going to care about them, and they could really whiz through to the other side of the room with absolutely no interaction. It'll be almost as if they're not interacting, they are almost massless, or they're able to really whiz through with very high speeds the way light particles do. So that's essentially the idea of the Higgs mechanism. That is, there is this field, analogous to the party workers, there's this Higgs field that permeates the entire universe. Every particle feels this field, but is affected in different amounts. And the more a particle interacts with this invisible field, the more mass it gets. But of course, if this field is invisible, how can we prove that it exists? Now, in order to answer that, well, the good thing is that the theory predicts that the field has an associated particle. And then this particle is what's called the Higgs boson, named after one of the scientists who came up with this idea. So what we try to do in our experiments in these colliders is to create the conditions that will allow us to actually produce the Higgs boson in our experiment. And then what we try to do using our data analysis methods is try to actually find the Higgs in our data. Of course, what was very challenging is that this theory that came about in the mid-1960s did not predict what the mass of the Higgs boson was going to be. So there was a very broad, diverse set of searches in these last 50 to 60 years trying to find where the Higgs might be. But that's not the only open question. There are several other open questions. And the first of these is, of course, related to understanding what we call this large mass hierarchy. That is, why are some particles, relatively light in comparison to, for example, one of the heaviest quarks that you see there, the big red blob, which is the top quark. Now, that's not the only question, because you've heard me talk about 3 generations of quarks and leptons. But why 3? Why is 3 a magic number? Could there not be 4 generations? That's a question we are trying to answer. And then if we look around us, well, there is an important question to answer. And this is related to what we call the matter-antimatter asymmetry in the world. At the time of the Big Bang, in principle, we were supposed to have equal amounts of matter and antimatter. What is antimatter? That is really saying that for every particle, there is an antiparticle, which is very similar in properties, except, for example, has a different charge. So an electron has an antiparticle that's called the anti-electron, or it has another name called the positron. So in order to understand that, let's imagine that there is an anti-Tom Hanks, and I'm using Tom Hanks because maybe you've seen this movie, Angels and Demons, which is based at CERN, which is all about particle physics. So let's imagine that there is an antiparticle version of Tom Hanks. In principle, Tom Hanks and anti-Tom Hanks would look very much similar. And if they were to come together and meet, they would essentially collide and annihilate. So matter and antimatter at the time of the Big Bang or soon after should have annihilated. But the point is, we are still here today and we are matter. So where has all the antimatter gone? It's really nowhere in sight. And so this is an important question we are trying to understand, the asymmetry between matter and antimatter. Then there is the question that everything that we know around us, all of the particles, well, most of this is what we call visible matter, and this comprises only 5% of the total universe. The rest of it is what we call dark, in the sense that we don't really see it explicitly. We can only infer its presence through its interactions. So what is responsible for this dark part of our universe, in particular, for example, dark matter? Well, are there new particles which are the solution and which will try to explain dark matter to us? And no, it's not Darth Vader trying to explain dark matter, but perhaps the Higgs boson could be related to the dark matter and that question. And not just that, so far you've heard me talk about the four forces that I mentioned. That is the electromagnetic force, the strong force, and the weak force. But I left out the fourth very fundamental force, and this is the force of gravity, which is in fact the most common force that we experience in our day-to-day lives, which keeps us, supplanted on this earth. That's a mug to sort of shows you the compact version of the standard model. And then basically it's really telling you that this current description of the standard model can explain all of the forces that I've talked about, but it does not include gravity. So the fact that the standard model does not include gravity is a big open question that we are trying to understand. In order to understand or answer some of these questions, theorists get together and they come up with very creative solutions to this. And then these go by a number of different names: supersymmetry, extra dimensions. I'm happy to talk more about it later. But there are several of these excellent ideas out there. Which of these might be correct? Well, we try to answer that by looking for new physics in our experiments. And we can do this in a couple of different ways. We have to figure out what the important questions are. We want to look more closely, which means we want to look with more precision, try to identify new techniques which give us that more precision. And then in other ways, we want to look in new places where we've not looked before. This sometimes means going to higher energy or doing new measurements. So this last part, which is going to higher energy, it is what the Large Hadron Collider at CERN has been looking at for the last 14 years. So the Large Hadron Collider is located at the lab CERN in Switzerland at the French-Swiss border. And essentially, it's a 27-kilometer tunnel underground, and you have proton beams that go in one direction and proton beams that go in the opposite direction. And they're made to collide at specific points along the rings, which is what you've seen here, where the detectors are instrumented. And the detectors watch what happens as a result of that collision, and that's the data that is collected. The Large Hadron Collider, or the LHC, has been running since about 2010, and it's been running at increasing energy over the years, ranging from a total collision energy at the start of 7 trillion electron volts to the most recent run, which started in 2022, where we are running at 13.6 TeV. That is close to the design energy of the Large Hadron Collider, which was 14 TeV. So that's the maximum the Large Hadron Collider can go up in terms of collision energy. So the larger the collision energy you're putting in, the more energetic the collisions that will happen, and hence the possibility of producing more massive, heavy new particles increases. What have we been doing with all of the data that we've collected so far? A large fraction of the effort has gone into really testing with precision the standard model. So the standard model has a number of predictions regarding all of the different particles that are known and part of the standard model. And this is a very busy plot, but it's actually also what I consider one of the most impressive plots coming out of the Large Hadron Collider, because each of those dots really is one measurement, or sometimes several measurements of a particular process. And what I want you to look at is the y-axis here, which is telling us the rate of the process in a way. And this is ranging all the way from 10 to the power minus 3 in a particular unit, which doesn't matter, but 10 to the power 11 on the other end. So they're about like, more than, 13 orders of magnitude is the range in rates of these different processes that have been measured. A lot of these processes, which are these points here, are compared to the theoretical predictions in this sort of gray band. And for the most part, we see that they match very well within the uncertainties. Of course, in many cases, the uncertainties are for the theoretical predictions, all the experimental predictions are rather large at the moment. So that means we cannot definitively say they agree with the standard model, but they are in that range of agreement, let's say, within uncertainties. So this is really a key to really testing the standard model. But perhaps the biggest sort of, history in the making result coming out of the LHC was the discovery of the Higgs boson. And this is one of those, historic moments, 4th of July, 2012, where almost every collider physicist can tell you where they were at that moment in time when the CERN experiments, the ATLAS and CMS experiments, presented their independent results of the searches for the Higgs boson. And what was really amazing to see that these two independent experiments, looking at independent data sets, both observed a bump in this mass distribution, a peak here, which indicated an excess of events of a particle at a mass of around 125 GeV with properties that we found consistent with the properties that were predicted by the theorists back in 1964. So, more than 50 years later, these experiments sort of validated that theory was indeed correct, that there was this particle, that it existed, and it could perhaps explain our big open question regarding mass generation. Of course, what have been doing since then? That was back in 2012. So we've really put in a lot of effort to really try and characterize with as much precision as possible the properties of the Higgs boson to try and understand, is it a Higgs boson or is it the Higgs boson as was predicted? And we do this by observing it in many different ways, by really trying to measure its properties of how it's produced, how it decays, and again, very importantly, measure its couplings to standard model particles, because as I'd mentioned, how it couples or how it interacts determines the particle's mass. And so this picture here essentially shows on the very top how what these couplings are and how large these couplings are. And we find actually that these couplings and their strength matches very well with what the masses of these particles are. So exactly what the standard model predicts seems to align well with what we observe in the data. However, if you look very carefully, so at the very top, this is a log plot. So if you look at linear, if the standard model predictions were to match perfectly with the experimental observations, you will have the data points align at 1. This is sort of a ratio. What we find is that the central value of these data points and the uncertainties are consistent with 1. But these uncertainties are quite large at the moment. And so imagine a scenario where these uncertainties shrink, that is, we measure this more precisely, then the big question would be, does the central value come at 1 and therefore be perfect with the standard model? Or does the central value in some cases, for example, here, remain away from 1? If it remains away from 1 and the uncertainty and the error bars shrink, then we have new physics, because we have found in our data that the coupling does not agree with the prediction. So figuring out precisely these couplings is really, really key to understanding the Higgs boson. But there are lots of other questions. Is the Higgs boson an elementary particle like the electron, or is it a composite particle like the proton? How does the Higgs interact with itself? Because the Higgs has mass. It must interact with itself, and that is what determines its mass. And then this Higgs self-interaction or self-coupling is related to what people call the potential energy of the Higgs, and understanding what the shape of this potential energy curve is really gives us fundamental understanding of perhaps the matter-antimatter asymmetry in the universe and what and how it came about. So there are critical questions which are related to understanding the Higgs self-coupling or the interaction. And there are lots of other things, such as, for example, how does the Higgs couple to muons? We haven't measured that yet. Are there additional Higgs bosons? Are there exotic decays in which the Higgs decays? So a lot of these open questions will be sort of answered or looked at. So where are we in this particular plan? We are right now at what is called the run 3 of the LHC. We're going to continue to take data next year. And after that, we're going into a period of an upgrade to the accelerator, which will provide more intense beams, and an upgrade to the detectors to allow us to analyze those intense beams. And then we will go into another era of data taking, which will last all the way till about 2040 or 42, where we will collect huge amounts of data. In fact, I would say that 95% of the total LHC data is still to come and be studied, and it will come in this period that's called the high luminosity LHC run, or the HL-LHC. So we're going to be able to do a lot of good physics with this data, and understanding and studying the Higgs properties certainly will be one of those. And we expect that we will be measuring the Higgs couplings to a few percent or lower for many particles. But as you can see here, this is a range of those couplings. Some we will measure better than some others. We will start to probe the Higgs self-interaction or the shape of the Higgs potential, but only to a precision of about 50%. So we will really not truly be able to answer the question of how exactly does it couple to itself. But we will start to make good progress in that direction. So what we are really looking for are new facilities that will really improve the Higgs measurements beyond the HL-LHC, which will give us a better idea of the Higgs potential, really to try and answer the matter-antimatter asymmetry question, and an understanding of really, is the Higgs boson truly the standard model Higgs boson? Can we definitively answer that question? So not just that, we're also trying to really search for new physics to try and answer some of the other questions I mentioned, dark matter, for example. And then these plots are very busy plots, but they are really showing us all of the different searches that have been happening at the LHC experiments. And what I want you to get out of here is the bars here, which go to, and this is a mass scale, in many cases, 1 TeV or a little bit beyond. And this is because the LHC, which is approximately 14 TeV, is a proton collider. You put 14 TeV in, but because proton is a composite object, you have only a fraction of energy available for the collisions between the constituents of the protons. And so the LHC allows us to sort of probe energies of the order of about 1 TeV or a little bit beyond it through indirect ways. But what we have done is we have said that there is no new physics yet in this 1 TeV scale. So what we really want to be doing, if we really want to answer all of the other open questions, we want a collider that is able to get to much higher scales, perhaps an order of magnitude higher in energy. And this is the 10 TeV kind of scale, which will help to definitively answer these questions. So what should this new facility be? Well, it should have this exquisite precision and clean production environment. It should allow us to measure the Higgs self-interaction. And all of the data tells us that we need to be able to probe more than 1 TeV. And this 10 TeV kind of scale would be really crucial for really as a step into the unknown as well as for physics targets. So to answer this question, we created the Department of Energy and the National Science Foundation created a sub-panel of an advisory panel. So there is an advisory panel called HEPAP, which advises the DOE and NSF, but HEPAP meets publicly and cannot have strategic prioritization, sensitive discussions. So they create a panel which then focuses on trying to prioritize all of the different particle physics projects to come up with an idea of what the DOE and NSF should support for the next sort of decade or so. So this P5 meets once a decade, reviews the size cases, and then comes up with a prioritization. This is sort of analogous to what other fields have called decadal surveys or long-range plans. So the last P5 plan was back in 2014, and so they created a panel in 2023. Who is the panel? Well, it's as a member, about 30 experts in the field from colliders, but also from other areas in particle physics. You can see me there on the left, and we met over a period of a year, and to come up with our deliberations and then take these decisions. As input, we took input from a process that's called the SNOMAS process, which is a community process which is led by the American Physical Society, which happened over a 2-year period from 2020 to 2022, which came up with a plan for, it's essentially a wish list of people saying, we want to do this because this is exciting science. And then the P5 had to take this input into consideration in coming up with the plan. And yeah, there were a number of community members, approximately 1,000, who joined this effort in person and in Zoom, and there were about 1,000 white papers that came about as a result of this effort. So during the P5 process, we organized a number of town halls at DOE labs where we really got to see some amazing work that is happening there. For example, construction of magnets for the high luminosity LHC. We saw how work is going on in the areas of cosmology, in the construction of neutrino detectors. We had virtual town halls to get information and interest from early career members, and a number of closed meetings and Zoom meetings that all happened over a 1-year period. Sometimes it felt like we were in these, dark rooms in the basement, trying to deliberate. But in reality, it was actually not that dark, but it was kind of similar. These are 2 pictures from 2 of our meetings, which shows our panel discussing. And the critical part of this was we had to prioritize the size cases, but under a budget scenario that was given to us by the funding agencies. So when we started discussing budgets, we had literally 11, 12-hour days to try and understand how to fit things within the budget. One quick word before I go to the budget is who the report is for. Well, the report is a roadmap. It's used by the funding agencies, but also by us to figure out where to spend our research time, how to prioritize. But it's also an advocacy document because we want to convince Congress to provide us money to actually do this exciting science. The report is not an implementation of the program. That is up to the agencies to implement it as they see best. What it covers is not just colliders, which is the focus of my talk today, but really a number of other experiments which study in great detail neutrinos, dark matter, cosmological observations, as well as, rare processes. What I will focus on in the next sort of, 5 minutes or so are really what comes after the HL-LHC question to answer what we've achieved and now where are we going. The budgets, as I mentioned, is really critical. If we look at the budgets, and then this is the y-axis here over a period of, sort of 10 years going up to 2035, all of the ongoing projects and the amount of money they take are in blue. If I look at all of the money that all of the projects that those 1,000 white papers gave us, the dreams that they want to achieve, that's in green. And this is not taking into account some major projects that we would build on the US soil, which would take even more. The scenarios that we were given by the funding agencies are given here in the blue and red lines. The blue line is what we call the baseline scenario, which assumes the CHIPS Act in the first few years, so an increase and then a steady sort of increase only because of inflation. And then the other less favorable scenario is where we don't benefit or take advantage, are able to take advantage of the CHIPS Act and just a steady sort of, inflation increase. So clearly, as you can see, the dreams as we started were not going to fit in the initial part within our funding scenarios. So we had to really try to figure out how we can make some of these dreams happen. And we detail in our reports how we go between these different baselines, scenarios and the less favorable scenarios. I will quickly, I think this is just to, basically a summary of what I just mentioned, but I also wanted to point out that the panel could not only just talk about building projects, we have to support students, postdocs, And then so we had to highlight operations and research as well, in addition to building of projects. And not just large projects, but also smaller projects where we can train students and postdocs. Another important thing to consider was that we cannot just do things on our own in the US. Particle physics is a global endeavor. CERN is currently leading with the LHC. However, the US is collaborating. Any projects that the US might take a leadership role in will require collaboration from international partners. So we had to take that into consideration in deciding where does the US have potential leadership and is competitive with respect to what might be going on in different parts of the world, and are we able to take advantage of US initiatives, and how can we do workforce development. So with that, we came up with the major themes that we wanted to focus on, and this looks at what we call deciphering the quantum realm, trying to understand in great detail particles such as the neutrinos and the Higgs boson that are still quite mysterious. Then next up, the invisible universe, the dark matter and dark energy questions that I posed earlier, trying to get to the bottom of that. And then perhaps, are there new particles and forces that can try to really explain some of these open questions? In order to do that, we arranged this in terms of what we call the main science drivers, and I will focus today on a couple of ones which are really important for colliders. Revealing the secrets of the Higgs boson, direct evidence or indirect evidence for new particles, and then determining the nature of dark matter. Before I go into that more, I just wanted to point out that the P5 vision, which has these physics themes, also wanted to balance current and future large and mid-scale projects, make sure we have a highly skilled workforce. We're taking advantage of computing and technological infrastructure and the global nature of particle physics to do our work. So with that, I will then talk about some of the projects that the panel recommended. And one of these is a major project in sort of the near to medium term. And this would be a Higgs factory. This would be an electron-positron collider that would cover the range of collision energy between like 90 GeV and 350 GeV. So at the Z pole, or at being able to produce a top antiquark pair. And the advantage of colliding electrons and positrons, unlike protons, that electrons and positrons are elementary particles, so their collisions are very clean and easy to sort of analyze in comparison. And this would allow us to have like an order of magnitude improvement in important Higgs boson measurements. Also do other model-independent measurements. We can achieve this using two kinds of machines. One are called circular colliders, where you have electrons going in one direction, positrons going in another direction, and making them in a circle and making them collide. And one such example is a machine called the FCC, or the Future Circular Collider, which will come at CERN after the LHC, or a long linear collider where you can just shoot electrons in one direction, accelerate them, and then analyze them at the end using a detector. And this is the International Linear Collider, or the ILC. There are pros and cons of the two, some differences. What P5 recommended was a Higgs factory. It could be either of the two to be built outside the US, because as you saw, in the next sort of 10 years, the ongoing projects completely take over our budget. And so we cannot have something on US soil, but rather we could partner with an international body outside the US and contribute in a big way to this. But looking ahead, I've mentioned how we want to really go to that larger energy scale, the 10 TeV energy scale. And that will really help us understand the shape of the Higgs potential and get to that new physics that's out there. And here, it's difficult to collide electrons because they have challenges associated with them, which means that we cannot accelerate them to very high energies. We can accelerate heavier particles to higher energies. And one such heavier particle that we've managed to do so are protons. But protons are not fundamental. That means we give 14 TeV energy into the LHC, we only get to about 1 TeV in mass access. in order to get to 10 TeV energy of mass scale for such as particles, we need to have 100 TeV proton collider. So a much rather massive machine. On the other hand, we could go to a lepton, such as a muon, which is heavier than the electron, but elementary, and therefore has some of the positives of the electron, some of the positives of the proton, and we can get to 10 TeV with a smaller machine. So there are several of these ideas to get to 10 TeV. So use the FCC ring to get to this large collider with protons, 100 TeV machine, but it needs many high field magnets to get there. So the technology does not exist yet. We could do it with electrons, but again, current technologies don't exist, but there's work going on. Or we could do it with muons, where the collider ring would be comparatively small, only about 10 kilometers. However, muons have several challenges. They are unstable, they decay very quickly, and we need to be able to produce, trap, and accelerate them incredibly quickly. We need to do R&D in order to do that. But if we are able to do it, we could have a compact collider, and a collider which could actually fit on US soil at the current Fermilab National Accelerator Lab. But we don't know if any of these technologies will be successful. So what P5 recommended was that we do R&D in all of these areas to figure out what might be possible in some 20, 30 years. I'm just going to end very quickly now. And so this 10 TeV collider could be on US soil, perhaps even. And this would bring what we call the energy frontier back to US soil. And this, of course, got people very excited, because there were a lot of news articles right after our report where people saw this as a potential future for the US, where Fermilab could be the site of this muon collider, a muon shot as it was called. And this really takes advantage of a lot of Fermilab's strengths. And we could do a lot of interesting physics en route to this 10 TeV collider, which of course will take, decades to build. It got people very excited. You can see the P5 panel all ready to cut the muon collider cake together with the Fermilab director here. It got young people excited. Here is my daughter wearing a muon collider shirt. And then, of course, the media that you may have seen, where they were all amazed that we as a complicated panel with 30 people actually agreed on a particular vision for the US. And so that was also an amazing experience personally for me. So with that, I'll end. So the P5 panel reviewed a number of interesting proposals for really excellent science from the community. We came up with a plan that really tries to look at delivering exciting physics, but within a sort of a budgetary constraint and within a global context. And we're hoping that this will enable fascinating discoveries. And in addition, we made some recommendations for really improving the health of the field, because people are really important to making sure that this exciting science happens, and that there will be hopefully exciting times ahead in particle physics. Thank you.
Thank you very much. Could you very quickly explain why when you do the collisions, you don't collect all the data? And I think you're the expert on that, the trigger mechanism or whatever. How do you decide that? And there was a very interesting thing that maybe you can help with. There are some of these particles they don't finish decaying as quickly, and that is one of the things the Large Hadron Collider cannot capture, is that delayed. Is that correct? Do I have that right? All right. What's the mechanism there? How do you decide what to collect? And what about those delays? Is that the thinking behind a new collider?
Great questions. Thank you. So the first is, yes, we have collisions which happen with large intense beams at 14 at 40 sort of million times per second is the rate of the collisions. We cannot write out data at that rate of 40 megahertz, nor do we have the money for all the tapes and disks we will need. So we make decisions very, very quickly using electronics and using software we write to sort of filter on interesting events. We do this by figuring out, using our knowledge of what interesting physics might be. That is, oh, it's potentially interesting if it has high momentum, for example, or multiple electrons and muons. And making those decisions very quickly in real time, we cut down the data and we store only of the order of a few thousand events per second. So 40 million, we choose about 2,000.
Oh my goodness.
And so it is critical, because what you don't want to be doing is that the events that you reject, you don't want your new physics to be there, because then you're potentially throwing it away. You're no way of going back and getting that.
Mm-hmm.
And in particular, the kind of new physics that you mentioned is exactly in that category, because these are particles we call sort of relatively long-lived, meaning that they don't decay right away in the detector such that we can identify their characteristics, but they may live a bit longer and decay in later. So we need to make sure we are not throwing them away in that initial filtering stage. And we could be, perhaps. And so we want to design future experiments which are sometimes looking in a very specific way for some of these signatures which might be coming from some of these long-lived particles, by looking at characteristics. For example, these particles might have certain properties, such as timing, which might be different from the standard model particles. So by designing detectors which can very, very precisely go after timing, you might be able to go after the long-lived particles. Some of it, the high luminosity LHC can do, but it was never designed to do exactly that. So now we have the opportunity with our future experiments to really design them in such a way that we can focus on extracting this new physics.
That's great to know. Thanks very much for that. You mentioned the muons anyway, and those are interesting. At Fermilab, they had the muon G2, and they made a big fuss about this and so on. But the muons seem to be very interesting, and you've already talked about them a little bit. But why are they so interesting? And is there anything special about the muon G2?
Great. So I'll first talk about the muons by themselves and the interest recently in using them to collide. So we've had two broad categories of colliders, where we have collided electrons and positrons, and we've collided protons and antiprotons. The problem with electrons is you can't get them to very high energies, because you lose energy through something that's called synchrotron radiation. The problem with protons is you can get to higher energies comparatively. However, they are messy objects because they're not elementary objects. So what they produce is a mess. Now, what we want ideally is a best of both worlds. A collider that provides a clean environment that is similar to the electron machines and can get to the higher energy that the proton machines can give you. So the muon collider is essentially that machine. It has the best of both worlds, which will allow you to get to precision Higgs measurements, get to the 10 TeV mass range in terms of the energy reach and searches for new physics. So it's the best case scenario, but we just don't have the technology today to make it happen. And so work is ongoing to figure out if we can do that work to create a muon collider in, say, a 20 to 30-year timeframe. The muon G-2 experiment is really trying to look at certain properties of muons to really, in a way that tries to understand some key questions from the standard model. So it's really looking at muons themselves, whereas a muon collider will collide them to see what comes out of the energy.
Okay, thank you for that. The other one is a long thing. I'm afraid it would take you a bit, and that's about building a collider in the United States. You know the story about that originally, but very quickly, if you can, this person would like to know, can the lessons learned from the failure to build it here be used to help justify building a US-based super collider?
Absolutely. I think we have to learn from our mistakes. And so I think there are lessons we've learned, and then we have people in our field who are aware. And some of these has to really start with having the right expectations to begin with, and coming up with a plan that's realistic, coming up with a budgetary scenario that's realistic, and then sticking to it. But it also means that you have to have global cooperation. So US, it's getting to the scale where the US will not be able to do it on its own. So we will have to have strong partnerships. We've been a strong partner to CERN and elsewhere. So we would have to get into agreements whereby other countries will partner with us. We have to make the case for this kind of science, because we need support from Washington, D.C., that this kind of science is as important. And I personally think it is, because it really answers some of our fundamental, questions about the world around us and nature, and therefore what all we get from there. So I think it has to be an effort which is multi-pronged, which we have to work on for years. It's not going to happen tomorrow, and that's okay, because the technology also needs work. So we have to work in parallel to make it happen, I think. But the fact that this committee of 30 people with different interests, they were not all collider physicists, right? They were neutrino people, they were cosmologists. We all emerged with this general sort of consensus that this was the exciting future for the US. Gives me confidence that we can perhaps, that the physics case is strong, really strong, and with that we can work towards making the case for the public and for the funding agencies and for Congress.
Okay. Dr. Bose, thank you very much. This is all very interesting, very important information, and I think digestible. It's hard to make this digestible for a non-specialist, but thank you very much for that. And I wish you the very best with all of your hard work over the years. Thank you very much.
Thank you very much. It was great talking to you all.